Okay, so yesterday we saw at the level of quantum numbers, of fitting the different quantum numbers of the particles we find in nature into a unified theory, that there was a very pretty way to fit the forces of the standard model into relatively small groups where they fit tightly, and more impressively, that if you do this, the fermions that is the quarks and the leptons fall neatly into multiplets, and that furthermore their funny hypercharges that in the U1 that appear in the describing the relative strength of the U1 coupling and are taken from phenomenology within the standard model and have funny values, that these all get explained. So these are remarkable facts. Maybe they're coincidences, but it's hard to believe that such striking regularities are just coincidence. And so we're led to ask whether there's some physical sense in which this unification is achieved, not just at the level of bookkeeping, but at the level of actually implementing dynamics and forces that would have the known forces all as different aspects of a single force, described by a larger symmetry. And the magic of the Yang-Mills theory, or non-abelian gauge theories, is that from symmetry one can derive dynamics. There's a unique way to go from the local gauge symmetry into a dynamical theory at the level of the vector gauge bosons, and then all you have to know about the fermions in order to get their couplings, or the couplings of other kinds of matter, is their representation in the case of non-abelian groups, or charges in the case of abelian groups, the strength with which they couple, overall numbers, one for each multiplet, discrete in the case of compact groups, of non-abelian groups, and just numbers in the case of abelian groups, like hypercharge, that tell about the strength of the coupling to the fermions. So it's a very specific framework, having got to the symmetries to get to dynamics. That's a very powerful connection. Gets us from regularities in the structure of particles, the group theory, if you like, to very specific models of how they interact. So we are led to ask whether this group theoretic organization, this unification at the level of quantum numbers, can be lifted to a dynamical symmetry, a non-abelian gauge theory that controls the interactions. At first sight, there seem to be two big problems with this. Well, one enormously big problem. It's one problem that has a two-step solution, is what I was aiming for. The big problem is that the first prediction that you get when you unify the interactions, when you have one symmetry group that relates all the different parts, the first prediction of that idea is that all the coupling strengths are equal. And, okay, there is a second big problem. I remember the logic I wanted to present. The second big problem is that if we make this unification, we get extra interactions. We have, for instance, in addition to the color gauge bosons that change one strong color charge, like a red charge into a blue charge in the strong interaction, or the gauge bosons of the weak interaction, the weak isospin gauge bosons, the W particles, that change one kind of weak gauge charge into another. We have things that change strong charges into weak charges. And when you work it out, you find that this leads to interactions that, for instance, change quarks into leptons, and vice versa. And if you work it out in a little more detail, you find that these interactions are capable of violating quark conservation, or also known as baryon number, so that they could induce proton instability. So if we really take this at face value and implement the non-abelian symmetry, allow all the possible transformations that these gauge bosons in the extended theory would allow, we would get proton decay. And if the couplings were anything like of the strength of those new gauge bosons, or anything like the strength of the existing gauge bosons, protons wouldn't live very long. They'd live comparable times to muons or something like 10, instead of 10 to the 30th years or so, or more, that they're known to be stable, they would decay in a microsecond. So these are two problems. And fortunately, though, we know we've met problems like that before, and we know mechanisms from the standard model itself that address these two problems. One phenomenon we met in the electroweak theory is the idea that gauge symmetries can be broken, and when they're broken, some of the gauge bosons become massive, the Higgs mechanism. They can be spontaneously broken by the existence of condensates, or in other words, when the stable solutions of the theory have less symmetry than these equations of the theory. And so we can imagine that, say, the gauge bosons that are in SU5, but not in SU3 cross SU2 cross U1, not in that subgroup, because of the influence of a very large condensate, sort of the Higgs mechanism on steroids with a much larger scale, get very, very large masses, and that can suppress the extra interactions. I'll return to this subject, but let me just say now that for this to suppress proton decay enough to be consistent with experiment, you need to find that the values of the condensates, the vacuum expectation values that break SU5 or SO10 down to this much smaller group that we see at accessible scales, you need vacuum expectation values, let me call it capital V since they're really big, of order 10 to the 16th GeV. This is to be compared with the vacuum expectation value that's about 100 GeV that we meet in the standard model. That gives masses to W and Z bosons. That's why I say it's the Higgs mechanism on steroids. It's 14 orders of magnitude larger condensation energy. Some people are frightened by this big number. They call it the hierarchy problem. But we, what? Oh, well, I should, this is greater than 10 to the 16th GeV based on you want the proton to live long enough. So you make these gauge bosons very, very heavy. Then the processes their exchange induces is suppressed. And to make them heavy enough, the condensate.
The age of the universe as a kind of a standard.
Well, no, people have done no. We now know that protons live much longer than the age of the universe. Well, they better, otherwise a lot of them would be gone by now. But the lifetime bounds are now at the level of 10 to the 32 years, compared to the paltry age of the universe of only 10 to the 13th years or so. Well, you measure big, big vats of water with, 10 to the 30 hydrogen molecules in them, and or H2O molecules, and look for little Cherenkov tracks as if the protons would take.
But then you said that some people are scared from that big number.
Well, they ask, where does this big number comes from?
Why is it scaring within the theory now? Like, where does one start?
Well, scared may be the wrong word, because people say, are you sure that if you have such a big number that there aren't intermediate effects, for instance, that would complicate the picture? Or, well, there are more specific. If you look inside the guts of the theory, so to speak, if you look at the details of how the theory gets implemented, you find that there are contributions to the vacuum expectation. The theory tends to pull these vacuum expectation values to be equal. So the challenge is to get such a big disparity of scales. Let me just leave it at that. It's kind of it's an important issue, but one that I didn't want to concentrate on in this lecture. But this will be very important to us, as we want to. We don't want to just pull this out of the air. We want to have some basis for producing such a large number on some other grounds than just we don't want protons to decay. Some more theoretical, conceptual grounds. Okay, so that anyway, that at least has the potential to address this question. Then the second question is addressed by another central phenomenon we learn within the standard model. That is the asymptotic freedom, or the importance of running of couplings, which is that the effective coupling of an interaction can depend on distance due to vacuum polarization. Therefore, we have the following kind of picture, potentially, and the burden of this lecture will be to show that this picture actually works quantitatively. Which is that at some very large scale, call it the unification scale, we start out with the symmetry unbroken, so it's a scale comparable to or larger than the condensate, so that the symmetry breaking effects are negligible. So this mu would be comparable to or greater than the value of the condensate. Then the couplings are equal to a good approximation. Okay. But then the condensate kicks in and the symmetry is reduced. And now when we calculate vacuum polarization, we'll get different contributions that don't respect the full SU5 symmetry, but only respect SU3 cross SU2 cross U1. And the coupling strength of the different interactions will start to diverge. I've drawn them on as a straight line. We'll see why. Well, for now, this just for simplicity. This is not meant to be a realistic calculation, but just sort of displaying the topology of the situation. So we have the strong coupling, call it G sub 3 for SU3, a G sub 2, and a G sub 1 for the different couplings. And then, now we get to compare with experiment at some relatively low scale, where we actually do experiments and measure the different couplings. We can see, do these agree? With observation. So that's the overall strategy. Taking a conceptual bird's eye view of this, we'll have three outputs of our calculation. If we follow out this logic, based on two inputs. So the three outputs are the G3 at some accessible energy, I'll call it Q0, some accessible energy momentum scale Q0, based on two inputs, namely the unification mass and one coupling, the unified coupling at the unification scale. Okay, because there are only 2 inputs but 3 outputs, this isn't guaranteed to work. Even if it does work, we have to go back and check, for instance, that the unification scale is bigger than this 10 to the 16th GeV. Otherwise, we're in trouble with proton decay. We also have to check for the consistency of the calculation, since we'll be calculating using formulas that are appropriate for weak couplings or not very strong couplings. That's the only time we can really compute. We'll also have to check that the unification coupling is not very large for the consistency of the calculation. And we'll also want to check whether this scale is so large that quantum gravity corrections come in. So there are lots of things to check. But even if we don't worry about those, we have an over-constrained calculation because we want from 2 inputs to get 3 outputs. So if it works, that's a genuine success. You're getting out more than you put in. Okay, so with that introduction, now let's get down to the business of how the calculation works. There's one important preliminary that we need to take care of. When we have non-abelian symmetries, the coupling strength has an unambiguous meaning. Because the different charges don't commute, I should say the normalization of the coupling strength. Because the symmetry generators obey nonlinear commutation relations. So you can't multiply the symmetry generators by an arbitrary constant and still obey the same commutation relations. In a less abstract form, the remark is the following. The way you couple fermions, for instance, to the fundamental gauge bosons is you change ordinary derivatives into covariant derivatives. So these will have the different gauge bosons and symmetry generators here. And in the case of SU2, for instance, that would be a familiar case. We'd use symmetry generators which, for spin 1/2, generate the spin 1/2 representation. In SU3, you'd extend that to, you'd use these 3 and 5 others to fill out the complete set. And these are invariantly characterized by having, or normalized, by having their trace squared equals a half. The trace is invariant under redefinitions of basis, so that's a thing you can use. You can normalize all the generators that way, and then you have an unambiguous normalization of what the coupling strength means. And so you can compare unambiguously the coupling strengths of a G2 and G3, and they should just become numerically equal to G5 when everybody goes to the unification scale, as long as you normalize all the generators by this kind of invariant condition. When you come to hypercharge, however, there's no such generator. There's just numbers out here. And we need a different way of relating the hypercharge that's measured in the laboratory, the conventions that we use when we describe hypercharged coupling strengths in electroweak phenomenology, to the hypercharge normalization we get by having generators within SU5 that satisfy this same trace condition. So, to get that normalization correctly, what we should do is take, on the one hand, compare, I should say, the trace that we get in terms of electroweak conventions to the trace we get from the non-abelian convention for our hypercharge generator as used in the SU2 cross U1 notation, the electroweak version versus the SU5 version. By the way, I should say that I'm going to be always referring to SU5. SO10 includes SU5 as a subgroup and really doesn't have to be considered separately. The unification works the same way. Now, in the electroweak notation, if we take the covariant derivative, it's normalized in such a way that we write a coupling constant called G prime, and then use the generator of weak hypercharge multiplied by a hypercharge vector boson, normalized in the normal way you normalize Maxwell fields with the Maxwell kinetic energy for that U1 field. Where this Y the hypercharge are these funny numbers that we saw yesterday attached to the different particles. So what we want to do is take the square of this thing, square of this overall coupling, and take the trace of the square as it applies to a multiplet. That'll give us the electroweak description of the trace squared, which we then should compare to the non-abelian version, in which the trace squared will just be the G5 coupling times squared times a half. So we're going to compare the trace we get here in a basic vector multiplet to the trace we get in the non-abelian version, where it would be the overall coupling squared times a half. This convention here. In that way, we can compare in a meaningful way the strength of the absolute strength of the hypercharged coupling to the absolute strengths of the non-abelian couplings in SU3 and SU2. Okay. So this is to be equated to G prime squared times the trace you get by looking at all the particles in the five-dimensional multiplet, remember, which was made from D bar and L. This one has three components. This was the anti-particle of the right-handed D quark. So it has three different colors. And the hypercharge is the average charge of that thing, which is simply plus 1/3. So we get three contributions when we take the trace of the square, 3 times 1/3 squared. And then from this one, we get hypercharge minus 1/2 for the lepton doublets. And so it has in the trace two components, each of which is a half squared. Okay, so this works out to be G prime squared times 5/6 is going to be equal to the non-abelian version of the coupling times 1/2. And that gives us the way to translate the observed hypercharged coupling G prime squared into something we should use in comparing with the strengths, the absolute strength of the strong and weak interactions, G5 squared. So at the unification scale, they all become equal, but I use G3 and G2 to describe the subsequent evolution of the strong and weak couplings. I'll use G1 to describe the evolutionary version of the hypercharge. But at the end of the day, it's supposed to be compared with 5/3, well, square root of 5/3 times the thing you find in the particle data book as the hypercharge coupling. Of the weak interaction. So G1, so G3 and G2 are, this is the strong coupling constant that you always see with conventional normalization. This is the weak coupling that you always see. And just to get things right, we have to compare, we have to get an overall normalization, and we have to use G1 equal to square root of 3/5 times G prime. I'm sorry, square root of 5/3 times G prime. Okay. That's a technicality, but a very, very important one. If you want to do things numerically, you have to get this right. It's the hardest part of the calculation. Okay. And but don't worry, if you didn't catch all the subtleties, this is something you can go back to, and we won't be relying on this for the rest of the calculation. Just comes up when we compare with experiments. Okay, so with that out of the way, let's now go to the structure of the actual calculation. Do the running of the coupling. Now, conceptually, as we saw, we should be running from small mass scales to large mass scales, or from rather small, comparatively small energies, like at the LHC, to much larger energies. We could do it in either direction. In practice, it's nicest to start with something you know and run things to higher energies, in which case we have to face the possibility that it might not work. You might find something like this, where they don't meet, or you could in principle even find something like this, depending. Or even no two of them ever meet. For three of them to meet in a point is a very special condition. And by the way, I've been drawing this in a very stylized way as straight lines. They're not straight lines. So all kinds of things might have happened. Okay, now the way the couplings actually run to lowest order, which is what we'll be discussing here, is the same in all cases. It looks as follows. There's an effective coupling, I'll just call it, and as I said, it applies to all cases, so we can define it like this, that depends on scale. Yes? That's 40 minutes already? Okay, let me just finish this thought and then we can have a break. The way the coupling runs is described by this kind of equation. Where the physics that's being described here, the physics that's being summarized, is the physics of vacuum polarization. The effective charge that your gauge boson sees is not only the bare coupling, but also includes, in a non-abelian case, you would have this bare coupling, but also includes the effects of virtual particles. And if you change the overall scale, you want to include, if you're working, say, with things that are have very, very large momentum transfers, and want to compare the coupling at smaller mass scales, what you would do is integrate out the effects of the virtual particles with all the intermediate values of the momentum. That turns out to give a logarithmic dependence on the scale, because the underlying divergences were logarithmic divergences. And you can see that the correction to the bare coupling is, so this is the new bare coupling. Sorry. Is cubic in the coupling itself. You could also, and if you want to do this in an abelian theory where the gluons, where the photons don't couple to themselves, or the hypercharged bosons don't couple to themselves, you can similarly calculate the renormalization effects on a fermion vertex. And again, you'll find cubic corrections. So to lowest order, to lowest non-trivial order in couplings, the structure of the renormalization group equation looks like that.
So the tree level doesn't contribute?
The tree level doesn't contribute to the derivative because it doesn't vary with Q.
Right. So this is the one.
This is the one loop correction, right? So if instead of allowing all momenta to if you integrate out the effective momenta between Q and Q prime and lump it into a new effective coupling, you get a correction that looks like this. Okay, and that's a very logical place to stop. It's all, yeah, so we'll take it up from here. We've now reached a very crucial point where we're starting to implement the underlying physics quantitatively. Okay, are there questions at this point? Okay, so 10 minutes for recreation and getting some food. All right. Yeah.
There, I mean, that's definitely a very important one. The future of it should be very smooth and silent way of all this stuff.
In fact, I visited the PhD circuit too before I leave PhD circuit.
Yeah, right. Yes, I had that in Beijing too. I'm now living, using
But of course, there's a problem more complex. Because the salary from the government, so it becomes more complex. But this unity can have some solution.
Yes, I mean,
because they can't wait the money from the government. If they wait from the government,
they have to think about a way how to deal with the problem, and then they have to get the funds from the government, and they have to find a way of financing that individually. Especially, yes, tickets and flight tickets, very many physicists, they don't have that.
They should have found a special way.
Right, not every time find a special.
For example, police they found a way. Okay, then for the next time they will found another way.
That's true.
That's what. Communication with the code and not paper.
Oh yeah, it's important with the WCC, and that's why I told them.
A good news.
Where is it?
The paper has
This is
been
the
accepted
first. This is the first.
Today by PRL.
Oh, congratulations.
The 4 hours ago, of course, publication is one of the address.
That's great. Okay. So, does that mean I can put it on my publication list?
But it's not yet. It's a PRL. It has 3 very positive reports, so it's not yet through.
Oh,
it will be through. There's no way. So don't put it on the list.
No.
2 weeks or so.
No, sure. Okay.
Another 1 hour.
Well, I'll try to keep it short than that.
So the student at MIT would,
We don't have yet a way for them to get the video.
so they will sit together, or they can
I don't
just
know.
watch separately?
No, it's separate. They're not gonna.
You don't have to watch at the same time.
No. Well, ideally, we would have telecommunications, but obviously that's not set up.
Other will
So we definitely want to have that.
We want to have that possibility, definitely.
Looks like it's already.
That's the goal.
Already a solution. Like the Phyllis indicated, they have.
It
one
does
model,
exist, yeah, right.
So it looks like that it can be
Yeah,
solved.
yeah,
It's just a
it
matter
can
of
be
time,
solved. Well, it's,
right?
yeah,
How?
there are, yeah, people have been doing this sort of thing for for years, but not very well. I think we can, now the state of the art is probably ready for a really smooth implementation. So we could set it up
Yes.
also with Sweden.
Yes.
Yeah, I think people will
That's 3 points.
be a very valuable resource.
Uh-huh.
All right.
I feel satisfied.
Three
with-
different continents.
Right. I keep telling people, Frank has been so successful and prominent in both North America and Europe. There's no reason he cannot be so prominent and influential in Asia, especially through China, and in particular through this city here.
Yeah, well,
So I don't see there's no reason why, and so long we provided the means,
yeah.
and so there's no question about that.
Okay, let's get started again. This main equation of the renormalization group to the so-called renormalization group to lowest non-trivial order can be rewritten in a way that's more transparent to solve simply by looking at 1 over g squared instead of g. And of course, it's just elementary calculus to show that this is minus 2 bj. Okay, when you take derivative of 1 over g squared, you get the derivative divided by g cubed, and so the g cubed just goes away. This is also very pleasant because if you rescale the fields, the gauge fields, so that the covariant derivatives don't have g's at all, the only place g appears in the Lagrangian is in the form 1 over g squared multiplying the trace of the gluon kinetic energy. And so that is sort of the natural universal coupling that appears. Okay. And this is an equation that is easy to solve. We solve it in the form 1 over gj squared. Of course, these gj's implicitly have arguments. They're functions of q. I could write it. Why not write it? The effective coupling, 1 over the effective coupling as a function of q is minus 2 log q over q0 plus 1 over the effective coupling squared at q0. Simple as that. And I'm sorry, and there's a bj, very important. bj that appears. Okay, so this plot I showed you with straight lines actually does represent the structure of the calculation if what I'm calculating is 1 over g squared and the scale is logarithmic. Then the running of the couplings, at least to one loop order, really will look like straight lines with slopes determined by these bj's. So we have 3 such equations. one for SU3, one for SU2, one for U1. From that, we can use two of them. Oh, I'm sorry. And then we run this up at Q equal to the unification scale, or let me call it QU just to have not a divergence of notation. We must have, this is the unification condition, that G1 that all the couplings become equal. They all become equal to the underlying SU5 coupling, if you like. One basic coupling governs them all, now that we've normalized things carefully. So that's a boundary condition here, that these are all equal. So by setting two of them equal, two of the right-hand sides equal at Q equals QU, we can determine what QU is. We determine if we subtract and reorganize things, we get the equation, for instance, comparing the weak and strong interactions, that 2B3 minus B2 log of QU over Q0 equals 1 over G3 squared at Q0 minus 1 over G2 squared at Q0. So this is an equation now for the unification scale in terms of the computable numbers B3 and B2 and the observed couplings G3 and G2 at some accessible scale Q0. Okay, and that's just gotten by setting the left-hand side of the equation with j equal 3 equal to the left-hand side of the equation with j equals 2 at the value q equals q sub u. We could also have compared the weak with the hypercharge coupling or the strong with the hypercharge coupling. We'd better make sure that all those equations are consistent.
The first equation that you started from, can you once more briefly remind me where that was coming from?
Oh, well, we had an equation of the form so it's simply, from here, it's simply a matter of calculus to show that.
Okay, I'm already
Okay, right. No, that's. Please do ask questions like that, because if you lost the thread for a moment, probably other people did too. Okay, now. So we have a consistency condition by comparing this equation with the indices 3 and 2 with a similar equation derived in exactly the same logic with, say, 2 and 1. And so we get another condition which is, I'll write it all out because it's sort of the high point of the logic of this calculation. So this now does not contain the unknown scale Q sub u. This contains, on the left-hand side, just computable numbers, and on the right-hand side, empirical constants. So this is a consistency condition, or if you like, a way of relating the three independent couplings of the standard model in a non-trivial way. So this is a crucial prediction of the whole idea of unification. Okay, this is the payoff, if you like. This is now, a lot of things could go wrong if there's extra physics between the low scale and the unification scale. That complicates the equations, or if the whole idea is wrong. But if the idea of unification in a reasonably straightforward way is correct, then we should have a relationship like this. Or I should say, if the unification in a minimal way is correct, we should have this relation. So, if it doesn't work, we say it's not, well, if it doesn't work, we're disappointed, but not too disappointed, because a lot of things could potentially go wrong. It could be all kinds of extra physics if we're extrapolating over many, many orders of magnitude of scale. But if it does work, that's really telling us something, because it's the straightforward consequence of a minimal implementation of the idea of unification. Okay. Now, to see if it does work, it's just a matter of plugging in what the B's are and comparing with what you find in the particle data book. Now, the value of the B's is a famous calculation which got some people Nobel Prizes. It takes the following form. In terms of group theoretic constants that I will explain. Well, maybe I won't explain them too much, because if you know this stuff, then explanation is superfluous. If you don't, you'll need some private study to really get it. But this is the Casimir operator for the adjoint representation. It's a group theoretic constant. And it governs the contribution of the gluons. The famous negative, the negative sign is asymptotic freedom here. The Casimir operator for the adjoint, and for SUN, it just takes the value n. And for U1, of course, it's 0, because photons don't self-interact. So it's usually written this way: Casimir operator for the group SU3, for instance, equals 3. And so forth. So this is the contribution from the gluons to vacuum polarization, things like this, that appeared in the renormalization group. One also has contributions from fermions, potentially. And what appears here is the trace of the representation matrix for the fermions, including all of them, with the normalization that I described, where in the vector representation the trace is normalized to be a half. And this is, so the 1/2 here just is referring to spin 1/2 fermions. And for this 4/3 is for Dirac fermions, that is complex non-chiral fermions. If you're dealing with Weyl fermions, there's a factor of a half, because there are half as many of them. And if you're dealing with Majorana fermions, that's also a half, because they're real instead of complex. And if you're dealing with fermions that are both Majorana and Weyl, it would be a 4th. But actually, those don't occur in 4 dimensions. Okay, and this is a similar thing for scalar particles that might occur. And this is the formula for complex scalars. If they're real scalars, you have to include a factor of a half. Other questions? Okay. So I will not step through in detail how you plug in the numbers for different things here, unless someone really asks me to, because it's spelled out in the notes. Very clearly, and I don't want to run too much over time. So let's skip to the answer, which I'll just record and then explain. For B3, as I said, this number is 3, so that's easy enough. And one has, well, I will go through it just in this case. For each family, so remember there are 3 families in the standard, known in the standard model, but we'll include that as a parameter just for fun. For each family, we have 2 fundamental representations of SU3 for the quarks, both of which are Dirac, because they come in left and right pairs. So we get 2 contributions to the trace, but the trace is a half, and so we just get the 4/3 for each family. So for the lowest family, this would be the U and D quarks, but then there would be contributions also from the higher families when we include those. And there are no colored scalars, so there's no contribution from this term. So that's the kind of thing you have to deal with. And I'll just write down the answer in the other 2 cases. B2, thank you. And the details are spelled out in the notes.